All right, hey, what's up, everyone? I am on the line on Zoom with Andrew Trask. Andrew is a PhD student at Oxford and leader of the OpenMined community. If that name sounds familiar, it's because I spoke to him on the podcast, episode number 241, Privacy Preserving Decentralized Data Science. Andrew, great to speak to you again. Great to see you. We were just talking about how the last time we saw each other, it was at NeurIPS a couple of years ago in Montreal, and it was cold. How you doing, man?
I'm doing pretty good. I'm inside and warm, not by the fire, but we've got space heaters everywhere, so getting the job done.
Nice, nice. And we are, it is what is today? It is the 20th of March. Relatively early on in everyone dealing with COVID-19. How are things in Oxford?
It is very quiet in Oxford.
Yeah.
So term just ended. Students are moving away, headed back home. It looks like pretty much all courses are going to be online for the foreseeable future, which is pretty
Mm.
crazy. And I think perhaps a defining moment for for higher education. It'll be interesting to see what happens. But yeah, and there's no toilet paper anywhere because that's
There
the
too, I
one.
thought it was only in the States.
No, everywhere. It started in Australia, I think. Yeah, no, that's the one thing everyone can't live without apparently. Like
Yeah.
bread, you know.
The currency of the future.
Yeah, exactly. Yeah, that's the great commodity to trade. If you find yourself held up at gunpoint, you go back and get a few rolls and
Flash some TP.
yeah, exactly.
Yeah, I hesitate to even bring that up, but I'm taking a cue from Jeremy Howard in his first Fast.ai course the other day. Said, hey, we thought about whether we should bring this up, but hey, it's the reality that we're all dealing with, so might as well, address it. And
No,
it's,
it's
it's
true.
definitely the reality that we're all dealing with.
Hmm.
But we are here to do a democast. Democast being kind of, take webinar and podcast, smush them together, walk through some code. And this particular one, we're excited to have you on to talk about PySyft. Maybe before we get to PySyft, you can refresh us on what is OpenMined and how did PySyft come out of that, and what is it?
Yeah, sure. So OpenMined is an open source community, and we're focused on really doing two things. So lowering the barrier to entry to privacy preserving techniques and tools, especially in machine learning, through free code, so through free software, Apache 2 licensed software, and through education. So we put together sort of courses and tutorials and community meetups and events to help people learn more about privacy preserving AI and privacy preserving tools in general. So PySyft, I would say, is probably our flagship privacy tool. To the extent that my background is in machine learning, and 3 years ago when we first got started, um, it, privacy kind of lived in different communities. To the extent that there were some encryption libraries that existed, like I think the Abby framework was there. Microsoft has Seal for doing like homomorphic encryption, encrypted computation. There was a handful of very small differential privacy libraries, and I don't even think the big ones had come out yet. And then there was rumors of kind of federated learning, but no code had been open sourced yet. And so it was one of these things where if you wanted to combine these tools and try to do sort of any type of machine learning or data science that incorporated elements from encrypted computation and differential privacy and federated learning, you basically had to roll everything yourself, right? They just didn't exist. And so PySyft is really born out of a desire to bring these communities together underneath a common tool set and a common language, and to secondarily make it possible for people who maybe don't understand differential privacy or fancy encryption techniques or whatever to be able to use these techniques via an interface they're already familiar with, meaning via the tensor interface. So
Mhm.
there's lots of fancy privacy tools that we try to bake into tensor types so that you just say, hey, add these two tensors together, and these tensors might be encrypted under the hood, and it's going to do all the protocol for you. Or you might say, add these two tensors together, and they're, in a hospital somewhere that you might not even be on site. It's gonna go control those tensors in a remote place and perform federated learning. Or you might say, add these two tensors together, and it's gonna try to track your privacy budget automatically and keep track of, how you're manipulating sensitive information, and really take these advanced concepts and bake them into this, this familiar tensor API that people are already used to.
Cool. And so what are you going to show us today?
Yeah, so today we're going to walk through basically just the fundamentals and kind of get to know the idea of what specifically we're going to walk through the PyTorch framework. What does it look like to do privacy preserving ML in PyTorch, right? So to the extent that PyTorch is this kind of NumPy-like interface that lots of people are familiar with and comfortable with, and it's my hope that we can paint a picture for what machine learning is going to be like in the future. And the big reason for that is that the world's most important problems involve the world's most important and valuable and sensitive, often, data sets. And so if our machine learning tools can give us access to some of this really important information, it really opens up totally new use cases and verticals and new research for all the users of PyTorch out there. So yeah.
And now what's your sense of the kind of the trend and the progress that we're making? I think when we spoke a couple of years back, we'd previously covered quite a bit of differential privacy, but it was, folks were talking about it for sure, but it wasn't nearly as popular a topic as I think it is today. At least I feel like I'm hearing more and more about it. Apple at the last NeurIPS did a presentation about how they're using it kind of in a lot more detail than I think that they've done previously. Are you starting to see differential privacy and privacy preserving machine learning, generally speaking, becoming more popular?
Yeah, absolutely. It's super exciting time. When we last talked a year and a half ago, we were in the realm of sort of research papers and prototypes, right? And then these prototypes were sort of like toy examples online. But right now we are in sort of 2020 is the year of industrial enterprise pilots and startups that are based around this. So I personally know of pilots happening all across, particularly healthcare and finance, consumer services. Obviously, big tech has already rolled out differential privacy and federated learning, and in some cases even encrypted computation to most people's phones and devices already. Many of these use cases have been proven out to be at scale. They've been proven out and are starting to get interpreted via new laws like GDPR. And we haven't quite hit the phase where sort of everyone can kind of jump in and interact with these yet. I think we're still on the way there. We're not quite there, but for right now, we're in the phase of those who have sort of significant means and risk tolerance, who are leaning into early edge technologies, are typically running pilots at about this point with this technology, which is super exciting, especially to have been kind of anticipating this phase for so long.
Cool. So if I'm a developer, how do I get started?
Yeah. Today we're going to be talking about, so obviously a library called PySyft. So if you want to get started, pip install Syft. So if you're looking for sort of more details, you can head to OpenMind's GitHub account, and you'll see PySyft, which is often up here at the top because it's very actively developed. In the README, you'll see various ways that you can install it. I highly recommend to install things using Anaconda or some other virtual environment manager, just because you'll find that we don't have to change your sort of base installation. So, just practice good Python package management hygiene, everyone. So shameless plug. We do also have Docker containers, this kind of stuff, but a simple pip install Syft inside of a virtual machine should be all that you need. Okay. And today we're going to be walking through a couple of sort of selected examples from our tutorials folder. So whenever we push sort of new code or new functionality that affects the front-end API, we sort of encourage our developers and core contributors to go ahead and create a notebook that teaches this new piece of functionality they did, just so that our tutorials try to stay as up-to-date as possible with new functionality. And actually, one thing I would sort of like to plug, recently there's been a huge effort to translate all of these into a variety of languages. So it looks like we've got
Awesome.
1, 2, 3, 4, I don't know, maybe a dozen or so languages that have partial or full support for all these. So if you want to walk through some of these tutorials and you're interested in privacy preserving machine learning, and it would be easier to read it in your native language of Mandarin or Hindi or any of these supported languages, I encourage you to jump into it. Yeah, but today we're going to start at the beginning. So and the beginning for SIFT is really about augmenting an existing deep learning framework. So when we were sitting down and saying, okay, how do we want to make the world privacy preserving, right? There's obviously the easiest thing to do is just start building your own thing, but the problem is that means first we have to recreate so many of the deep learning tools that people are using, and secondarily, even if we made something amazing, we would have to convince people to sort of learn an entirely new API. And that's just a bigger barrier. That doesn't fill the spirit and intent of our community, which is to lower the barrier to entry to privacy preserving machine learning, not create a big stack of list of things that you now have to do in addition to all the other things you used to do, right? So what we're going to see here is a snippet of the functionality that this single line sort of executes. So we import Torch, we import some Torch dependencies, whatever we want to have accessible. And then we run this thing called the Torch hook. And what the Torch hook literally does is it goes through and extends and modifies the Torch API with new tools for remote execution, differential privacy, and encrypted computation. And the general design principle in PySyft is just that you want to remember is that everything is a tensor type. And the reason that we choose that paradigm is because people know how to use tensors. People know how to add groups of numbers together, perform matrix multiplication, back propagation, autograd, all these kinds of things. This is what people are familiar working with. So yeah, that's what we'll be walking through.
Okay, cool.
So step one is just, got to run the first cell. Step one, import Torch, and then run our Torch hook. So as you can see, like when we do this, Torch should still feel like we're at home. We're still operating the same normal interface that we normally would. Yep. And the second thing we do is we introduce one core new primitive. So if you're familiar with deep learning frameworks of any variety, the core primitive is the tensor, right? So everything is just a big nested list of numbers, and pretty much everything we do is based on an API on top of those. And we might build things that use tensors, so convolutional layers or different optimizers, so these higher level objects, but everything passes through the abstraction of a tensor. So the second primitive that we introduce that is not present in current deep learning frameworks is this notion of a worker. And a worker is just a location of a machine that's actually going to run our operations, right? So in our case, for our examples, we're going to use a virtualized version of this. So we can just call virtual workers, which are all going to run on my laptop. But you could envision this worker being a pointer to a machine sitting in a hospital, sitting in someone's smartphone, sitting in a browser desktop somewhere, sitting in a Raspberry Pi on a buoy in the middle of the ocean, right? And the full version of this, and actually I'll plug one more thing in a second, is that these workers, in the future, you're going to pip install access to millions of these workers.
Yeah, I was just going to ask, looking at the way you're referring to this thing as Bob, is there like a pets versus cattle kind of metaphor here where you've got these workers that, you're deploying individually, but is it also appropriate for the scenario that you're describing where you're managing them as a field of workers or a mass of workers as opposed to individual ones?
Exactly. That's I couldn't have expressed it any better. So if you're interested in seeing how these kinds of get deployed in these sort of large groups where you can say, I want to do a search for diabetes data sets and then coalesce those into sort of one object that I can work with. That's what this PyGrid platform is all about. And this is this is the scalable server. This is the thing you deploy to the cloud or to a Raspberry Pi or to a private on-prem data center. And it subscribes to, it's basically a mega worker, right? So we're going to use this virtual worker for the intents of like testing and teaching and development, but it's exactly the same API as if I was sending something, across the planet to a ship sitting in the middle of the ocean.
So it kind of abstracts all the workers and you just deal with it like it's a worker, but your work is actually going to many. Okay, cool.
Exactly. And it just makes it easier for us to work with stuff, right? And while at the moment we don't have any like public data networks that we're hosting at the moment, within 2020 we'll start actually hosting sort of these public data networks where you'll pip install access to PyGrid, and you'll immediately be able to search for interesting data sets that you can work with on remote machines.
Okay. And I see a reference to Kubernetes there. Are you doing kind of remote edge federated deployment of Kubernetes?
So the PyGrid is pretty flexible in general. So there is one sort of Docker and also Kubernetes focused deployment where you can do these kind of beefier nodes. I don't actually believe that Kubernetes is like for like Internet of Things related things the most relevant thing. And then also for some. I probably shouldn't leave this without mentioning for smaller devices, we actually have device specific workers that are often light clients. So this is like a Kotlin one for being able to sort of build Android apps, and then the Swift one should be around here somewhere. SwiftSift is for being able to add this functionality and run a worker from inside of an iOS app. Obviously, because obviously edge device is like a really big deal. And again, the idea is that like any operations that you're performing here that you're packaging up and you want to be able to send to a remote machine and execute there should all be super fluid. Like from our standpoint, we don't really care where the execution environment is happening. The sort of SIFT protocol, it might be running in JavaScript or in Kotlin or in Java or in XYZ other language on the remote worker. But here, the interface that we get is PyTorch.
Okay, cool. So then we're creating a couple of tensors.
Yeah. So that was a lot of abstractions. Let's play with stuff, man. Okay. So we create this worker, we create a couple tensors, and then the first method that we extend PyTorch with is this send method. Whoa, which I just promptly deleted. And what this does is returns back to us a pointer to the remote object. So as you can see, I have me. This is my ID of the pointer that's sitting on sort of me as a worker. And then this is a pointer to an object that's sitting on top of Bob's machine. And because these are virtualized workers, we can actually take a look inside, right? And we can see, we got one tensor that's 1, 2, 3, 4, 5, and one tensor that's 1, 1, 1, 1, 1, right? Which are the two tensors that we sent to Bob. But the really incredible part about this, and the price that's sort of nice and intuitive, and I'll just pop out here just to show it with autocomplete, is that we have access to sort of the full PyTorch API at this point, right? So nothing has changed, and this
tensor is on Bob's machine.
Exactly. So even though for all intents and purposes we have no access to the data, and like it still feels like the data is on our machine. So we can do things like we would normally with PyTorch. And of course, the result of our operation is not the data itself, but as a pointer to the remote information, to the remote data.
And now where's the actual mapping to another physical machine happening? You just created this virtual worker and you gave it an ID. Where's Bob?
So in this case,
you should call that Waldo.
Yeah, where's Waldo? I like that. I'm totally going to steal that. Or hey, pull request, welcome. So in this case, this worker is actually sitting, because it's a virtualized worker, it's sitting within the same Python runtime, right? So because in an abstract sense, a worker is just a collection of tensors that I can refer to, right? Like this dictionary is what the worker is, and the only thing that's sitting on top of this is a bunch of APIs that allow me to manipulate these tensors. Okay. And so for our intents and purposes, it's here, but we could do a socket worker, we could do a worker across multiple threads, we could do a worker across multiple machines or across multiple clusters, right? And it's sort of abstract away. And actually, a piece that we're working on right now is making it so that you have one worker endpoint, and even in the background, it can be load balancing across multiple different machines. So you're accessing, say a hospital data center data set, right? But there's 100 different machines, all that are doing different tensor operations in the background, and it's automatically load balancing that in front of this sort of worker interface, right? Okay. So it's really our interface to data, and even though it's running on this machine, for all intents and purposes, it could be anywhere. And of course, more importantly than even the physical location of the data, what Bob really represents is a notion of control, because what we're really saying here is that this is Bob's domain, right? And so that's why when I said a second ago, like this could be a pointer to a whole cluster of workers that are Bob's workers. What we really care about, and when we start getting into the more detailed features that PySyft provides, like the security level of like when something leaves Bob's machine and we need to check the differential privacy budget, or we need to make sure that like all the permissions are allowing something to leave, right? This is the core primitive that we are adding to the deep learning framework, the notion of domain. And all the tools that we want to use, like differential privacy and encrypted computation, sit on, like, help us navigate how things move in and out of that domain of ownership, if that makes sense.
Yep.
So as we can see, we added these two tensors together. The result was Z, which is a pointer to Z object. As we can see in Bob's objects now, there's a third tensor, which is the result of our computation. A few things that it's important to sort of think, like this pointer has certain things, like pointer location is the pointer to the things that we're doing. Obviously, Bob equals the pointer location. We can see what the ID of the object is at that location, and then we have this notion of an owner. So now each tensor does not exist in isolation. Each tensor has some sort of domain that's claiming it, right? It has some sort of area that is its. And this is where there's one thing implicitly that happened, which is who is this me object? Who are we sending stuff to? What does my domain look like? And so implicitly inside of PySyft, it always assumes that you yourself actually are a worker. And when you send something, it is leaving your domain and going into someone else's domain, if that makes sense. And really just this, we can go through a bit faster. We can see, really important feature. So I'm going to send two tensors to Bob. I'm going to add them together. There's the result. Now I want to see the result. This very special and super important method called .get. And .get requests access to whatever is being pointed to. And so when we think about permissions, and we think about differential privacy, where it actually needs to be enforced, and we think about tensors that might even be owned by multiple different people, and we have to actually make sure all of them authenticate through it, right? Security really revolves around making sure these .get requests are fluid. And there's two things that we want to achieve sort of long-term on our roadmap for these .get requests. One is to make sure that obviously it's secure. So tensors that are private, even though I can manipulate them on the remote machine, I can't look at the results by itself, right? Like by default. However, if I do make a .get request on a private tensor, like one of the projects we're working on right now is the ability for that to be popped into a compliance queue, or what we call a compliance queue, in, say, the hospital. So like, let's say I'm doing some data science, I've got my remote machines, I'm doing stuff on the hospital, Z equals X plus Y, A equals Z times Z, I'm doing back propagation, I'm training models, I'm manipulating lots of remote tensors. Ooh. And now let's say A is some sort of aggregate statistic. It's like the accuracy of my model, something that I want to see, right? So I'd make this request, and instead I would get an error back. And it would say, oh, whoa, hey, this is private information. You can't look at this, right? And normally this is where the huge amount of red tape exists in the world right now, right? Where people have to dedicate a portion of their life to get access to, say, medical data, right? Yeah. And it's because this part is really, really hard. And so if what we think is the most important process is to make it so that when you call .get, it can get popped and a compliance officer can pull up in an app the data you're looking for, see all the context around it they need to be able to see to make a well-informed decision, and say, yeah, he's allowed to look at the accuracy of his model. And then 10 seconds later, I call .get again and I've got it, right? And this is the fundamental bottleneck. If this becomes secure and performant and widely used, this is how we get Kaggle level collaboration on like the world's private data.
That sounds so simple, but so hard.
It is a lot of work to get it right, and it's even more work to get people to trust in it, right? To work through the initial pilots.
Even the UI UX of this, like I run get the first time and nothing happens, but 10 seconds later I'm just gonna run it again. Like, how do I know that it's ready to run again? Like, is that a book extension, or is just so many little details there that are super interesting.
And actually, so to your point, with that being hard, if you pop over into our roadmap repository, you'll see that basically the roadmap for 2020 is not a list of features that we want to build. It's a list of use cases that we want to partner with someone to deploy. And the reason that we want to do that, and often that's for free, like to actually help them deploy something, and like our team of 70 core people can help them do it. And the reason that we want to do that is because we want to get this feature exactly right.
Yeah.
And the way that we get this feature exactly right is helping someone do it and walk through with their business people and the high level people who are responsible for protecting their data, and get them to the point where they feel confident and they understand exactly why this bottleneck is going to keep their data safe while allowing them to extract as much value as possible from it.
Do you think there's only one version of getting that right? Meaning, how use case dependent do you think that's going to be?
So I think that it's less likely that there's going to be like major classes of things, and I think it's more likely they're going to be knobs that people want to configure in slightly different ways. So I think we can build kind of a one size fits all interface in general, but where people will have different parameters that they care about more. For example, so like for the automatic differential privacy tracking, right? This is basically saying like we have some sort of mechanism that is going to keep track of the maximum amount of private information that you could possibly get out through a .get request, right? And so I think that there's a certain threshold where someone could say, look, if it's below an epsilon of 0.1, for the whole project, we don't care. Just call .get and it's fine, right? Because we have some sort of trust in the system to say, like, if you're just, if I'm getting like an F measure for evaluation over a data set of 10 million data points, like nothing's like we can have reasonable, we can lower the friction for data scientists to work with this data. By allowing this tool to sort of allow .get requests that are underneath this threshold.
Right. So not only do you have this kind of framework for, I mean, the key is that you've got this ability to gate the requests, and you gave the example of like it popping up on someone's phone, but once you've got the framework, you can build some rules around that so that not every request is going to pop up on the person's phone. The ones that are above the margin. Interesting. Exactly. So you mentioned you've talked kind of thus far quite a bit about privacy budgets and things like that. I'll just throw in a pitch, a reference for a show that we did earlier this year on the podcast, Practical Differential Privacy at LinkedIn with Ryan Rogers. Good show. We talked about some of the things that LinkedIn's done internally to actually a paper that they presented at the last NeurIPS. To manage their privacy budget across multiple requests.
Very cool. That's awesome. Yeah, and really getting it right across multiple requests is the hard part. And also modeling like how much do you think different people are going to share information, for example. So like in this case, do I have a maximum of 0.1 epsilon just for this data scientist? Or is that for anyone who's touching this data? Meaning if I spend 0.1, someone else can't spend 0.1. And that comes down to whether you think we're going to compare notes. Like what's our likelihood of doing that? Like what's the level of trust that you have with me as a user, which is frankly why, sort of anonymous data markets is such a hard problem. Like there's a non-trivial number of projects that have kind of built this future of kind of blockchain level decentralization. Everyone's data is sort of registered on the blockchain and everyone's doing every use case with it. But the problem is that like you really
privacy budget.
Exactly. Because basically you have to assume everyone is worst case, which means that you have to have the most restrictive version of your privacy budget, which means no one can learn any really useful insights, right? So having a more liquid understanding, a more nuanced understanding of your level of trust with different actors and also their identity to hold them accountable is a really, really important piece of context. But yeah, and after this, in terms of this demo, is really just about saying like the full PyTorch API is here. So we can, send two tensors to a remote machine. We can do stuff. We can call back propagation. And if we get back a gradient, we can also see like the gradient. So like the full PyTorch API is here, right? This is about being able to do remote, to utilize the full PyTorch API on a machine to which we don't have direct access, right? Other than this whitelisted set of methods.
And are there any corner cases or limitations or API restrictions, or is it basically the entire PyTorch API you can use remotely?
So this one, there's no restrictions. For some of the encrypted computation ones, there will be more restrictions just because the encrypted computation protocols, you can only do the parts of the protocol that we have an encrypted computation protocol for.
Okay.
So if you use a type of encryption that, say, doesn't do encrypted multiplication, then that changes the things you're able to do.
Okay.
If that makes sense.
Cool.
Yeah. So I think most of the conceptual work is actually here, even though it's like a really simple demo. And now we can put them together into like sort of more end-to-end use cases. So if, let's say I have some code here that does just normal training. So this is just straight up normal PyTorch. It trains a model. If I instead take my data, so I'm gonna create some data, right? I'm gonna split it into two sections. So Bob's data and Alice's data, right? So I've got these two workers, and I'm gonna send Bob his data and send Alice her data. And now I've got this sort of data sets collection. And so this is a collection of pointers to now remote information. Obviously, this is not how you'd set it up. You don't like start with all your patient records and disseminate them to hospitals and then start working with them, right? But just so that you can kind of fluidly understand what you're working with, you start in kind of in the familiar area of I have everything, and then distribute it into a setting that is an ideal federated learning setting, just to kind of get a topology as sort of why we construct the tutorials this way. Did I not? Oh, I forgot to
skipped a bunch of.
I skipped a bunch of stuff. Got too carried away teaching stuff. Cool. So now we use a standard optimizer. And now this is exactly, I know it's a little block of code, but this is actually exactly the same code we were running a second ago with two differences. Model.get and model.send, right? So we're going to run normal PyTorch code, but the only thing that's different is we're going to make sure that when we're performing the weight update for the model, that it's in the right location, the same location as the data, right? And so we can run train, and it basically trains in exactly the same way, right? Because it's moving. Now, this does not use sort of federated averaging. So a nuanced, important thing to recognize in the federated learning paper is that federated averaging actually has you train simultaneously on multiple different data owners, and then average the models after an arbitrary amount of time, right? So this is like
here we're pulling all the data to one place and then training.
This one we're training on one and then pulling the model back, and then training on another and then pulling the model back, and then training on another and pulling the model back. So if you look at like this, so we send the model somewhere, we train, we pull the model back, and then we take the model from the first. So this is the synchronous version, whereas the federated learning advantages for performance are much stronger in the asynchronous version. It's actually why some people do federated learning, not because they care about privacy, but just because they don't want to aggregate the data. Bringing back models is a lot less network I/O than bringing back, say, massive sensor data from 10,000 buoys out in the ocean, if that makes sense. Because you can imagine like a temperature sensor sitting in the ocean for all the time, taking like it just ends up being a lot of data that you don't necessarily. Another use case is like we just published a blog post on is like a maintenance for major components of like manufacturing components. Like if you build jet engines, for example. So like Boeing keeps track of all sorts of analytics about the engines while they're flying around in the sky, so that they can do all sorts of interesting things.
And one of these classic IoT examples where they've got like, how many, like 2,000 sensors in the engine, and they're collecting data, fractions of a second. There's a ton of data that they're
exactly. But yeah, like that like optimizing car engines for performance when they actually get out on the road, and you learn how people are actually driving with it, like all these kinds of things.
Okay.
So yeah, let's see. There's another tutorial here, which you're welcome to look at on the website. As I mentioned, these are here for advanced remote execution tools. It just talked about some of the more advanced things that you tend to do when you actually get into engineering cryptographic protocols. Because what we have here is a generic way to engineer how tensors should compute and move across a whole host of workers. And there's some more advanced things, like how do you tell tensors to go directly from one worker to another worker without stopping through you? Because like send and get means everything's coming through you. So we have this other one called move. And then this is sort of the more traditional federated learning with model averaging, right? Where we can we sort of I won't necessarily run it all, but the general premise is that we will actually forward prop and back prop both of them, and then average them after a certain period of time. But same general idea, same general tools, but just to show that you can kind of do this with a PyTorch like API.
And so we're doing all this, the examples kind of presuming these virtual workers. Once you get out in the real world and you're dealing with like network latencies and things like that, you've mentioned some of the architectural implications on that. from whether you're training your models distributed or you're pulling the data back. How does that play in the this federated training example?
Yeah. So for this one, it's a really important question. So let's go back to the very beginning for a second. When I take these sensors and I call .add,
Yep.
it sends a message to Bob and executes that .add, and it waits until add is done, and then it says, here's a pointer to your result, right?
Yep.
So if I'm doing federated learning, I'm sending all sorts of messages. I mean, it's like because I'm sending one message per execution, right? Which is great for flexibility. It's dynamic, right? In that sense, so it's a dynamic API for execution, which is very PyTorchy, right? It's very sort of in line with what PyTorch normally does. However, if I'm sending this halfway around the world, I don't want the latency, to your point. So for that, we have this thing called
if you already
plans.
know what you're going to do next.
Yeah, exactly. And also machine learning does the same thing over and over and over and over again. So yeah, it's a really obvious thing. Like, wouldn't it be nice if you could pre-send your computation and just say, hey, do this thing 50,000 times and tell me when you're done, right? And that for that, we have a thing called plans. And I think actually the name plans...
You plan for that.
Yeah, we plan. I see you've done this podcast thing before. But yeah, and actually, I can't even take credit for the word plans. I'm pretty sure it's in the first federated learning paper. They call there's plans as well. Okay. But really, this is just a decorator
for that.
Yeah, with the drum kit. You got to get yourself one of those keyboards, where you can do all the different sounds. Yeah.
We've got this portable mixer that has those buttons.
Do you really?
Yeah.
Is that like the mega pro level of podcasters? Once you get past 300 episodes, something like that,
you know what, we got that when we did our conference. We did a conference, TWiMLCon AI Platforms, in October, and cool. we wanted to do. We had a community hall, and we wanted to kind of make the podcast, integrate the podcast into it. So we were just pulling folks up and like doing impromptu podcasts in the middle of this conference, and
that's awesome.
That fancy mixer with the soundboard,
the fart sounds and everything.
Exactly.
Oh, Jeremy, Howard, golly, man, not again. Oh, I'm sorry, Jeremy. I hope I didn't take that personally. He doesn't have any sort of affinity for that more than any other human, to my knowledge. You just mentioned Jeremy, so he was top of mind. There's nothing behind that. Don't read into that. So we're planning. Yeah. We've got big plans, and really plans we package as a method, right? And the idea here is just, if you've got something you want to call that's, perhaps akin to the train method that we had before. Was it where we were doing intro to federated learning? This kind of train method. I just want to call this a bunch of times, right?
Yeah.
Like pack it into a PyTorch method, throw on the decorator, and now I've got a plan, and I can send that plan to a device like I do here. And execute it as if I was executing any other method. So I call it on pointers, it returns pointers, and the whole thing works. Some stuff that's in the pipeline for right now. So PyTorch released this really, I don't know if you're familiar with like the PyTorch JIT, the JIT compiler that allows you to take PyTorch graphs and compile them statically. So this came out, a while ago now. I guess it probably was PyTorch DevCon. So it was probably, it was before DevCon. It was probably a year at least ago. Okay. But so now soon you'll be able to actually compile these straight to JIT if you're only doing methods that are compatible with the PyTorch API. So you'll get a sort of an extra added level of performance. And the other thing that's worth mentioning is that this is what allows us to also do federated learning across mobile devices. So like a mobile device can sort of pre-download this, and then it has sort of how I do a weight update. Because sort of for security, we made a decision. You'll notice that like this virtual work interface is nice, but it's totally centralized orchestration, right? Like I am telling workers what to do when I want them to do it. And when you do federated learning with mobile phones, it's not really how you want to construct it, because because phones are constantly connecting and disconnecting, and or people will disconnect from Wi-Fi, like or they'll pick up and take a phone call, or actually in case of mobile phones, you really only want to do federated learning when they're connected to Wi-Fi and they're plugged in, because it's such a big drain on your battery and this kind of thing. So if you have workers that are going to have really diverse uptime, what you really want to do is pre-send a plan and tell it, hey, contact me with weights when you got them, right? Download models whenever you want to, update them and send them back to me. But here's the computation you need to be able to participate when you're available. And so we sort of use plans in that regard, and we can compile them to JavaScript, iOS, and Android, being Kotlin and Swift.
Okay.
So yeah, it's good stuff.
Cool.
So let's take a totally left turn. So that was all about remote execution. So the other part that I thought we would talk about today is encryption. And specifically, we're going to talk about, I think, what to me is the most interesting version of encryption, which is secure multi-party computation. And the reason this is really interesting is that let's imagine for a second that you've got 5 hospitals, right? And they each have data sets relating to skin cancer, right? But they don't have necessarily enough data by themselves. And actually, this is relatively common. Each hospital will process a few thousand skin cancer patients a year. It'll be really good, high quality data, but maybe not enough to train like a deep learning classifier, which are really data hungry. So normally, using sort of prior to something like these tools, you'd have to kind of decide if these were to enter into a joint venture together, right? You have to decide, okay, who's going to be the one that actually holds all the goods, right? Who's going to be the one to train the model? And you might say, well, federated learning. So everyone will hang on to their own data. I think, great, fantastic. So model goes down to the first hospital, it trains, comes back up. Model goes down to the second hospital. Oh, did I say blockchain?
I thought that's what you would say. Blockchain. Put it on.
Blockchain. Yeah. It solves everything. We talk about just sprinkle it over. I poured out my last bottle, but more's coming in the mail soon. No, actually, so blockchain is actually really good for append-only logs and stuff. I do like blockchain for that. But for like doing deep learning computation, like blockchain, so there was this great paper from like 2 or 3 years ago. Sorry, side tangent for a second. This great deep learning paper a few years ago, right when smart contracts were big, and there was kind of the first big sort of blockchain AI boom, and like SingularityNet did their ICO, and a few other projects were also pushing it, and someone did a paper asking looking into whether you could train MNIST on the Ethereum blockchain. And as I recall, the paper never really got as far as it probably thought that it did, because the key finding in the beginning was that just uploading MNIST to the Ethereum blockchain was going to cost $300,000 before you even did like a single forward prediction, much less a weight update and like iterating through the whole thing, like just moving the data. So yeah, blockchain is great for a lot of things, but deep learning is like compute hungry, data hungry. So it's like you're probably not going to do it inside of a smart contract. And I was like, there's more like zero knowledge proof stuff now, and I think there's some cool things you can do between federated learning to like check things in, which we'll get to in some time in the future. Anyway, side tangent. Back to our story. We've got 5 hospitals, right, and they want to go into business together. And the solution is federated learning, fantastic. So we'll send the model down to the first one, it'll train. Send the model down to the second one, it'll train. We average these models together. Oh wait, now we want to sell a prediction, which is how we're going to make money from this, right? All of a sudden, these banks have lost the ability to enforce billing for this shared asset, right? These 5 different hospitals. I think I said banks. Yeah. Five different hospitals created this derivative asset, this model that only these 5 hospitals could have created through their joint partnership, right? But everyone's got a copy, right? And maybe they're like just hunky dory and nice, and like everyone's like, well, just sell it. We're all selling it, so it's fine. But maybe one of them's, a mega hospital center with tens, hundreds of thousands of customers, and the other one is like a specialty skin cancer shop, right? And the the joint venture made sense because this one specializes in cancer, had lots of data, and this one has just loads and loads of customers, right? The odds of like 5 sort of neutrally ones is relatively small, right?
Yeah.
So then the question is, how can we allow this, and better facilitate this kind of joint venture where there isn't this inherent risk that one of them will simply run off with the asset, because it's totally undetectable. It's like music piracy, right? As soon as you send a copy to someone, they have a copy and they can copy it and copy it and copy it and copy it, and you will never, ever know.
Mm-hmm.
And so the truly extraordinary thing about secure multi-party computation is not the thing that you will read if you go and look at it on Wikipedia. Like if you go look, let's look at secure MPC, secure multi-party computation, Wikipedia. Right, if we go to Wikipedia and it says secure multi-party computation is a subfield of cryptography with the goal of creating methods for parties to jointly compute a function over the blah, 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 blah. Okay, so like TLDR for this, sorry, that was my best British accent, by the way, four years of experience living here. Sorry, this is all focused on the function, right? This is all focused on multiple people can jointly compute a function while keeping their inputs secret. Okay, that's what this is about. Super useful, like totally valid for like lots of interesting use cases, but it's not about jointly comparing functions, right? What secure MPC is really about in this context, if I can get back here, is about multiple different institutions, multiple different entities sharing ownership and governance of a digital asset, right? It is about long-term storage and long-term shared ownership and shared governance of a data structure, right? Such as a data set.
Us that?
Oh, I totally am going to show you that. Are you kidding? It's all in this notebook. Anything can be done in a Jupyter notebook. I know. I've been talking a lot. More coding, less talking. So first I'm going to show you how it's done sort of naively. This is not using PySyft, but I just want you to see how the innards work. Okay. So we've got this variable x, and we want to share it amongst 3 people. Okay. So and it literally is this simple. The first thing we do is we generate 2 random shares, okay? Random numbers. And the third one is a share that's created in a certain way, such that when we add these shares together, and mod q, like a large prime, it returns back 25, right? So these are my shares. And if I were to sum these shares, mod q, it doesn't work. Mod q, I get back 25. Right. So this is called additive secret sharing, and it is quantum proof, and and it is cryptographically secure. And in this case, looking at this, each shareholder has to participate in any computation or any decryption exercise that is done with this number 25. So like when we take this number X and we split the shares and we give those shares to 3 shareholders, those 3 shareholders now have control, joint control, and any one of them has veto power over any possible computation or decryption of that value, right? And it's not very interesting when one person starts with the number, right? X equals 25, because he already knows what it is. Like, who cares if it's shared amongst them? But where it's really interesting is when you create a derivative asset off of, out of things that the different shareholders bring to the table, right? So what we'll see down below in a second is like, if 3 people bring data sets to the table and generate in an encrypted space, shared ownership over a model, like a cancer predictor. Like, this is really novel, right? This is really, really powerful because this is shared ownership over IP, right? That is not just enforced by a contract, right? It's enforced cryptographically, which is really, really, really quite something special. So this was encryption.
Just to make sure I understand what's happening here, is the idea that the share A, share B, and share C here, which we're seeing all in one cell in a Jupyter notebook, would be happening by distributed parties.
Exactly. And if only we had a tool that allowed us to manage different tensors that were on a host of different machines all at once, if you can see where we're going. So just to get a little bit more familiar with, did I not run the decrypt cell? Oh yeah, a little more familiar with how additive secret sharing works. I can encrypt a 5 and a 25. And literally, if I add the shares together correspondingly, so meaning the first worker adds their shares together, the second worker adds their shares together, the third worker adds their shares together, mod q, then I can add these numbers together. And I can perform computation while these numbers are in encrypted in a shared state, right? This is, I just love this. I think it's so cool. So secure MPC to me is like, here's the amazing thing. Lots of people have heard about, homomorphic encryption, right? Secure MPC can do everything homomorphic encryption can do and more, right? Like it's inherently flexible. Like you can think of these shares as everyone having a private key.
What is homomorphic encryption?
Oh, homomorphic encryption, it's the ability to compute on encrypted data that's sort of more, it's more familiar to people because the encryption decryption process is sort of more intuitive because it's more like normal encryption. So I can take a file, I can encrypt it with a private key, or a public key, and I can give it to you. You can do computation with it and give it back to me, and then I can decrypt the result. And like that's homomorphic encryption. So it's like public-private key cryptography, which is like a little bit different than this. But this is basically where every share is a private key that each person hangs on to as a unit of enforcing their ownership over this asset. If that makes sense. So they're highly related. Basically, homomorphic encryption is the sort of offline version of secure multi-party computation. So like homomorphic encryption requires more compute, so it's going to require a beefier GPU, whereas secure MPC is going to require a faster network. So it's going to send a lot more messages over the network because you're constantly sort of moving shares around to implement each individual protocol. But in expectation, well, I'm using that term loosely. If you look in the literature on encrypted deep learning, in practice, between two powerful cloud machines, say in Amazon Web Services, secure MPC just absolutely smokes homomorphic encryption. Like there's, I think the state of the art is a 13x slowdown for doing encrypted prediction relative to normal prediction between two machines that are on Amazon. And that result is from, I think, May of last year. It's actually quite an old result. And as I recall, that result was using a synchronous communications protocol. So like I think the theoretical limit is like 6x slowdown, which is really, really nice if you have a fast network.
So now in your encryption function here, it is relatively simple. It's not using the kind of math that we typically associate with encryption. Like I'm not seeing like, huge strings of XORs and things like that. What is this just a model for, what you would actually use, or is this?
So it does get more complicated. Like, don't get me wrong. Like, but on the whole, secure MPC is a bit more approachable, a bit more friendly than encryption. Partially because additive secret sharing is so simple. But so a few things to call out. This is integers, and I'm doing this on integers, and I'm not showing you this on floating points because it does get much more complicated to do this on floating points. So the naive thing that's kind of the state of the art and state of our APIs at the moment is to use fixed precision arithmetic. So if everyone remembers back to their programming 1 and programming 2 courses, talking about how arithmetic was originally done for older processors, we didn't have this ability to move the decimal point around to take advantage of our 32 bits sort of most strategically. So we do have to use sort of fixed precision conventionally so that everything is stored as an integer under the hood, and then we just decide how much precision we want and we do computation. Funny enough, actually, the same technique that some of these like TPU instances are using to be able to go so fast, right? Because they can do really, really fast arithmetic. And as it turns out, the deep learning model doesn't care as much, and it appreciates the speed pickup a lot more than it is annoyed by the loss of precision. Yeah. Okay. So yeah, basically, you can do it with this. Multiplication is also quite a bit more complicated. Like I'm picking the simplest possible part of the API for the simplest possible algorithm because that's the best one to, I think, intuit and explain it with. And the comparison operation gets a lot crazier, which is a sort of a core primitive. And then for nonlinearities, you typically have to do some sort of polynomial approximation or some other functional approximation to get it to work. So it's not all sunshines and daisies for the whole thing, but really our goal is to like expose a tensor-like API that makes this happen. But enough waiting. Let's check it out, right? So let's say we've got 3 shareholders: Bob, Alice, and Bill. All right, so I'm going to create my torch hook. Now I've got my torch tensor 25, so we'll do the same example before, but instead of calling .send like I did before, now I'm going to call .share, right? And what .share does
it's a multi-party send.
Exactly. So now I've got 3 pointers to 3 different machines, each which are holding the shares of this number on those machines. And now when I call .get, what it does is it calls .get on each one of these remote shares, adds them together and mods them by that prime that we saw. And the important thing from a governance standpoint is that means the same processes we were using with .get for pointer tensors is now under the hood in here, where each, Bob, Alice, and Bill each had something pop into their UI where they had to approve it. Or Bob, Alice, and Bill, it was underneath the differential privacy budget, so it didn't matter and we were okay with it, right? So all these, because everything is at the tensor API level, these things can kind of interplay with each other and we get these nice, clean abstractions, right? We have a security layer that's keeping track of differential privacy and all these kinds of things. And we have this encrypted computation layer that's able to sort of enforce joint governance so that everyone who needs to participate in decryption decisions is able to do so.
Awesome. Can you scroll up like 3 lines?
Yeah.
Now I don't see where you specify the encryption function. Is that implicit in
.share? So yeah, .share always means sort of secure MPC share. And right now everything is additive secret sharing. At some point in there, you'll be able to say protocol equals blah. But right now we're basically making those protocol level decisions for you. For MPC, we're probably just going to keep making those decisions for you. The only things that will actually allow you to change, there are some threshold schemes. These ones are super cool when you start thinking about like governance and your head goes off in the blockchain space, because the one that I showed you, everyone, it's unanimous governance, meaning everyone has to participate to allow it. But there are also threshold schemes where say 60% of
quorum type system.
Exactly, 30%, 40%, 60%. And this is also nice if you're worried about someone running off with their share and like leaving the other parties hanging with no digital assets anymore, or if you're worried about them just being offline and you want to make it so that only 60% of people have to be online at any given point to do the encrypted computation with the asset. So I think these are the kinds of knobs we'll lean more into, and we'll try to make good encrypted computation decisions for you under the hood. And the other version of share, and I definitely want to plug this. The PyTorch team released this awesome library called Krypton at PyTorch DevCon last year, and Krypton is basically optimizing the craziness out of secure MPC. So like this is sort of like low level server to server, making it as fast as possible in PyTorch. And that will also be an optional backend that you'll be able to use inside of PySyft. So the idea, and it's a really synergistic relationship, because basically they know the guts of PyTorch really, really, really well, and can like engineer all sorts of really cool low-level optimizations specifically for the server-to-server environment. Whereas we kind of focus on the holistic story of like having these general purpose workers that could be any different type, and the flexibility of having multiple different backends. And we have like data search functionality and integrates with the differential privacy stack, all this kind of stuff. Whereas they're going like hardcore, sort of like what NVIDIA does in CUDA, right? Like we make these operations as fast as humanly possible. So definitely check out the Krypton library. It's super cool. But yeah, so and of course, in the same spirit as what we had before, like while these tensors are encrypted, we can still utilize the PyTorch API and even better, put modules above it and use it's like we can do encrypted multiplication, matrix multiplication, comparison operations, which are important for things like ReLU. Here's an argmax computation that does multiple different comparison operations.
Execute plan.
Such a good, I am so excited about this piece of functionality, and unfortunately I can't show it to you yet because it's not done in the way that I want it to be done. Like there is a prototype and I could show you something that looks like it, but like so the thing about plans is and slow me down because I'm way too passionate about something that's like mega nerdy.
Philosophical direction. The thing about plans.
The thing about plans is, and I will try to make this super brief. Plans are a method, right? It's a method designed for one person to do one thing over and over and over again. What we want here, this is a protocol. This is data being sent to other people in a coordinated fashion, right? That needs to happen asynchronously, right? So we are building this thing called protocol that is just like plans, and you can just basically specify some computation, throw in a decorator, and it should work. But what it really does is it sets up a graph of computation that is across multiple workers. It's almost like a pipe that goes through multiple different workers. And you can just pipe data through as fast as possible, and all they'll execute asynchronously. And the really cool part is that it's gonna work, basically across any version of this virtual worker interface. Meaning, when I take a computation and I define it in PyTorch with my specific model that I really like, right? I can deploy this between a phone and a Raspberry Pi and a data center, or 3 data centers, or a data center and a web browser and a mobile phone, and it doesn't care, right? It's just going to pipe it all through as fast as possible. Huh?
Or a grid of...
Oh, yeah, absolutely.
It's like Pied Piper.
Yeah. Yeah, it is like that. And yeah, so and those will be kind of the core design primitives of PySyft. Like, those are all of them. Like, everything is a tensor. Everything uses the worker interface. All computations can be stored as plans and present to make them fast, and anything can be packaged as a protocol. And if it's packaged as a protocol, it can run across any platform. That's like the SIFT spec, and then everything else is just building more backend workers like PyGrid and like scaling it up and all this kind of stuff.
Sweet.
And just to finish big, here's like the demo which you can go play with, which takes a PyTorch neural net and encrypts the values and then trains it while the values are encrypted. So you can go play with this and see how it works. There's this one additional method which we didn't talk about, which is fixed precision, which basically takes a floating point number and turns it into something that's an integer under the hood, so that MPC can share governance over it. But as you can see, even though everything's encrypted, this is still using all the standards sort of PyTorch.
Yeah.
Yep, exactly. And that's a big deal. Like the fact that it looks the same, the fact that that I shouldn't have to relearn. Like, it's good to intuitively have a high level understanding. Okay, it's shared governance. There's shares and multiple people. Like, got it. But like, I don't have to learn the cryptography protocol. I don't have to go through all the crazy different proofs and differential privacy to keep track of what's going on. And right now, if you want to implement a differential privacy system by hand, you literally have to go through and be like, okay, I'm going to do a sum, and I'm going to add noise, and I'm going to do it this many times, and okay, epsilon plus this plus this plus this. Okay, that's 2.7 epsilon. That's too much. Okay, go back. Like, it's literally like in like a pad and paper kind of system, right? And our hope is that this will do for privacy and these privacy tools what AutoGrad did for deep learning, right? Before AutoGrad, everyone had to hand engineer all of their gradient computations, right? And so it meant that basically it was PhDs only, right? Because just doing this sort of advanced partial differential equations by hand and not getting it wrong for arbitrary convolutional, LSTM craziness was just unwieldy. Like in doing it, forget about doing it in industry. You're going to redo that for every single customer that wants, a slight modification. And the implementations were often wrong because you had to do like gradient checking and all sorts of this crazy stuff. But when Theano was released, and TensorFlow after it and PyTorch after that, this is when everybody was able to do advanced deep learning because of this function right here, dot backward, right? So much intelligence is baked into that. And if we are successful in making encrypted computation, remote computation, in making it possible to answer questions using data that you cannot see, right? Answer questions using data while that data remains in the possession of someone else, right? What that means is that overnight, that ability will endow the world with 3-4 orders of magnitude more information that they can access on the world's most important problems, on cancer research, on dementia research, on diabetes research, on coronavirus research, but not just on that, also on like helping consumers understand themselves, right? You want to talk about data that's sensitive but that is really important. Imagine what if when you go to buy a water bottle, that you don't just buy it and go, oh, it's the Sistema brand, it must be amazing, right? Which is basically a proxy for every rumor you might have heard about Sistema.
That's like a martial art.
Oh, really? It says Sistema. Yeah, I don't know. This is it's my wife's bottle that I commandeered so that we could chat and I wouldn't get thirsty. But the notion that maybe instead we have some sort of data pipeline that makes it so that my garbage can keeps track of things that I throw away. And so when I go and buy this bottle, I look at 10 different bottles and I go, ooh, that bottle, everyone seemed to throw it away a week later. So I'm not going to buy that anymore, right? It doesn't matter how good the marketing is. It doesn't matter if they sent me, 10,000, like what the fake Amazon, reviews were, or whatever else, right?
Mm-hmm.
I know that people were throwing this bottle away. And the reason that I know that is because we had infrastructure that made it possible for me to learn that piece of information from data that I never access, which is what are people throwing in their garbage, right? Mm-hmm. And so there's this new field, which I'll plug now, called structured transparency. And I hope beyond hope that it will replace the word privacy, because it really gets at what we care about. Like, privacy is easy. Privacy is stupid simple. You want to have perfect privacy? Delete all your data, right? Like everyone has a key purpose built for it on their laptop and on their phones, right? As easy as possible. But that's not what we actually want. What we actually want is to learn important things while making sure that we don't learn other things. And if our tools are naturally endowed with the mechanics and the infrastructure that are necessary for this, right? And someday I pip install access to an open grid of the world's information that is like, everything from the world's garbage cans to cancer documents to whatever. We get a world that is simultaneously better informed about itself, a world with more truth, while at the same time being better protected from malicious uses of information, right? We get to have our cake and eat it too. And that's really what this infrastructure is about. Like, it's not about, it's not about the, fancy cryptography or just cool demos. What it's about is endowing the world with more truth, right?
Yeah.
And the ability to answer questions on data that they can't see.
Cool. Well, Andrew, that seems like a great place to park this one. Thanks so much for taking the time to walk us through that. Very cool stuff.
Yeah, my pleasure. And thanks for having me on again. Really appreciate it.
Great to catch up with you again.
You too.